Hi, my name is Erwin Wang. Today I'll be presenting our research work, Logic Shrinkage, Learn FPGA Netlist Sparsity for Efficient Neural Network Inference. This is a research collaboration between Imperial College and Cornell University. Neural Architecture Search, or NAS, automates the process of DNN design, but existing NAS methods do not expose the low-level flexibilities of FPGAs during architecture search, leading to potential underutilization of hardware. To address this issue, we propose logic shrinkage, a fine-grained neural architecture search methodology for FPGA netlists. Neural architecture search automates the process of DNN design, delivering FPGA-based deep neural networks with area efficiency comparable to hand-designed networks. In many NAS works, candidate functions are placed in parallel to form supernets, as shown on the left-hand side. After training the supernet using an ML training framework such as TensorFlow or PyTorch, the salience of candidate topologies are evaluated, and only those found to be of higher salience are retained. The final network topology is then transformed by an FPGA synthesis tool into a netlist, which is mappable to the target FPGA. The figure on the right-hand side shows the FPGA netlist of a real deep neural network, with each node representing a Boolean function. However, here is a problem. The network topologies we instantiate in ML training frameworks on the left-hand side are made of compute nodes in the form of dot products or matrix multiplications. However, we know that on FPGAs we have k-input lookup tables, each of which can perform an arbitrary k-input Boolean operation. Due to the separation between the NAS training process on the left-hand side and the FPGA synthesis process on the right-hand side, low-level flexibilities of FPGAs are not exposed to the architecture search process, leading to potential underutilization of the FPGA platform. So here is a question. Can we perform NAS by directly learning a netlist as the topology? To approach this question, we proposed logic shrinkage, the automated search for and construction of DNN inference topologies featuring learned netlist sparsity. To be able to learn an efficient FPGA netlist using NAS, we need to first make an FPGA netlist trainable under ML frameworks, so that the NAS fine-tuning techniques can be applied to the netlist. In our previous work, LUTNet, we took a sparse binary neural network, or BNN, and replaced the exclusive NOR gates with trainable K-to-1 Boolean operations. We named this process logic expansion. This is one example in which the netlist of a deep neural network, in this case, a binary neural network, becomes trainable. And we achieved improvements in area efficiency compared against the BNN baselines. This work was published in FGCM 2019. However, the FPGA netlists generated by logic expansion still do not fully exploit the spatial flexibilities of FPGA platform. In logic expansion, we manually specify K, the number of inputs per LUT. Choosing appropriate K in advance is challenging, and doing so at higher granularity, say at layer-wise granularity, is a time-consuming and error-prone process. We therefore propose logic shrinkage, a netlist pruning methodology enabling K to be automatically learned for every LUT in a neural network. And finally, I'll show some of our experimental results with logic shrinkage. Let's start with logic expansion. In BNNs, LUTs are used to implement exclusive NORs. However, K-LUTs or FPGAs can compute arbitrary K-input Boolean operations. So logic expansion is the process allowing us to relax this constraint and embrace LUTs' full expressiveness. Logic expansion further enables us to make use of the extra LUT inputs and perform more operations per physical K-LUT. In logic expansion, assuming a BNN layer is fully unrolled, we can harden the trainable parameters W's into LUTs binary masks, such that no external BRAM connection is required. This operator, therefore, becomes a wire for W equals to 1 and an inverter for W equals to 0. This truth table is, however, just a subset of the complete one-LUT truth table. Logic expansion, therefore, is the process of expanding the operator's truth table to span the complete truth table of a LUT. This LUT-based architecture really suits FPGAs because this network is the FPGA netlist. From exclusive nodes to LUTs, we increase the expressiveness without costing any extra hardware. We can further make use of the extra input ports provided by FPGA KLUTs, such that each LUT can express more complex binary operations. Logic expansion for KLUT produces 2 to the power k trainable parameters, which can produce up to 2 to the power k possible Boolean operations. But how can we train the netlist? Gradient descent requires a continuous backward function. In LUTNet, this is achieved by interpolating the Boolean forward operation with Lagrangian interpolating polynomial. In this slide, lowercase symbols represent data in floating point position, and uppercase symbols represent data in binary position. We take one LUT as an example. In the forward function, we have 2 trainable binary weights, C1 and C-1, hardened in LUT. In the backward function, these 2 weights are trained in real values using this function, which is a continuous expansion to the binary forward function. This 3D plot of output against weights visualizes the relationship between the binarized forward operation represented as the dots and the continuous backward function represented as the mesh with a given input x. This figure shows how the backward function interpolates the discrete binary forward function and enables gradient descent. Netlists generated by logic expansion are not ideal. Here, let's take the training of 3 LUTNet as an example. We start with logic expansion, leading to the generation of netlists we see in B. While B makes efficient use of the LUT expressiveness of each 3 LUT, it keeps K fixed as 3 per LUT. This is bound to be suboptimal. B, as a microarchitecture, is capable of performing all possible 3-to-1 Boolean operations, and there are 2 to the power 3, which is 256 candidate functions. But in reality, we may not need this high level of logic complexity. There is bound to be redundant logic in this architecture. Therefore, we propose logic shrinkage. Given our success in making a netlist trainable, we then remove the less important LUT inputs and make the netlist more efficient. This process leads to the form we see in C, in which each LUT has its own learned Boolean operation with learned number of inputs. We evaluate the salience of every single LUT input and remove those who are less important. If all k inputs of a LUT are gone, then the LUT is also removed. This architecture takes advantage of the FPGA's spatial flexibility and achieves a much higher logic density. Existing salience criteria, unfortunately, won't work with netlists, since inputs to the same LUT are interdependent due to LUT nonlinearity. Recall that in logic expansion, we made the truth tables of all LUTs real values so that they are trainable. Here, we can take advantage of the LUTNet's real value truth tables. On the right-hand side shows an example of our salience criteria. This is the truth table of a 2-LUT with real valued entries. After binarizing the entries into -1, -1, -1, +1, it becomes clearer that this will be implemented as an AND gate. The advantage of having real valued truth table entries is that this allows us to quantify each input's relative importance to the output. This is achieved by summing the changes to the truth table, which are caused by a change in each LUT input. Here we see that LUT input x1 is more salient than x2. LUT input pruning also requires a non-standard approach. The removal of an input from a k-LUT can be achieved via manipulating all of the 2 to the power k number of parameters into ignoring the input. In our previous example, if we were to say remove the less salient x2, we can change all c hat parameters into c hat prime using these functions on the left-hand side. These functions essentially make pairs of the entries equal, thus transforming the 2 LUT into a 1 LUT by ignoring x2. As you can see on the right-hand side, the post-transformation truth table would have identical rows, meaning that flipping the values of x2 does not change the output. After binarizing the entries, we get -1, -1, +1, +1, meaning that the LUT is now just a wire between x1 and the output. While the above example with k equals to 2 is straightforward, the complexity of these operations increases exponentially with k. To ensure scalability, pruning methods must take advantage of GPUs and DNN training frameworks. We achieve this by implementing the transformation functions with matrix vector multiplications, using a square matrix kernel U as shown on the right-hand side. This is the general form of the square matrix kernel U, which removes the ith LUT input from a k-LUT. This diagram shows the workflow of mapping the logic shrunk netlist onto FPGAs, with the logic shrinkage process highlighted in red. The users provide model, dataset, activation precision, compute node sparsity, and LUT input sparsity to the TensorFlow-based training software. The compute node sparsity controls the sparsity of LUTs, and the LUT input sparsity controls the aggressiveness of logic shrinkage. The trained network is directly compatible to the implementation flow of our previous work, LUTNet. Thus, we use LUTNet's implementation flow for logic shrinkage. Now, let's have a look at some experimental results. To capture the general trend in area accuracy trade-off, we construct Pareto Fronts of the 3 microarchitectures: RepNet, which is the BNN baseline, standard LUTnets, and logic shrunk LUTnets, with the initial k fixed at 4. The benchmark here is the CNV network classifying CIFAR10 dataset. Here, we take the accuracy of unpruned RepNet as the baseline accuracy, which is indicated by the small triangle on the left-hand side. The Pareto front of the standard LUTNet has shown significant improvements over the BNN baselines. And on top of that, the logic shrunk LUTNet implementations can further achieve up to 1.61 times area savings compared with the standard LUTNet at the baseline accuracy. Let's zoom in to look at the individual netlists. We tuned the k values from 2 to 5 and captured the area occupancies of Pareto-optimal Netlists before and after logic shrinkage. These netlists achieve the same level of accuracy as the baseline accuracy. The blue bars represent the Pareto-optimal pre-shrinkage netlists, with k fixed at 2, 4, and 5 for every LUT. The purple bars represent the Pareto-optimal post-shrinkage netlists, which were shrunk from k equals to 2, 4, and 5, respectively. As k increases, the area gap between the pair increases, indicating that pre-shrinkage netlists become more and more redundant as the fixed k value increases. The purple bars stay relatively consistent, indicating that logic shrinkage removes this redundancy. On the right-hand side, the power consumptions of the same implementations are separated into static and dynamic power utilizations, with dynamic power sharing the similar trend as area and static power being relatively consistent. In order to better understand the source of our area savings, we inspected the post-shrinkage distribution of LUT sizes. This table shows the breakdown in LUT sizes across logic shrunk netlists with more aggressive logic shrinkage towards the bottom. The majority of LUT counts per row is shaded in gray. We can see that there is a downward and rightward shift in LUT counts, meaning that logic shrinkage automatically searches for sparse netlists which use smaller LUTs. The top 1 test error rates shown in the table are averaged across 5 random trials. The error rate even decreases initially with increasing input sparsity before going upwards again. This supports our observation that the logic being removed from logic shrinkage are indeed redundant. To justify the effectiveness of our proposed LUT input pruning strategy, we also made a comparison against randomly pruning the LUT inputs. And as expected, our pruning strategy outperforms random pruning consistently, achieving up to 1.5 times area savings at the same level of accuracy. To show the generality of logic shrinkage, we performed experiments using multiple DNN benchmarks, ranging from small-scale MNIST to large-scale ImageNet. In this table, we show the post-implementation LUT requirements of each of these model dataset combinations, comparing the pre- and post-shrinkage architectures. For CNV classifying CFAR10, our use of logic shrinkage saw an area reduction of 1.54 times. With the smaller datasets, the gains were smaller. The MNIST and SVHN benchmarks, being smaller benchmarks, are more tolerant to sparsity. Thus, the majority of nodes in these networks were already removed during node pruning, which has happened before logic shrinkage. This has left us with relatively little room for further improvements by logic shrinkage. Despite this, we still achieved area reductions of around 10% for these simpler tasks. For ImageNet on BiReal 18 network, the baseline implementation without logic shrinkage was too large to fit on our target FPGA. With logic shrinkage using node and LUT input sparsity of 30% and 75% respectively, we were able to reduce the post-synthesis area utilization by 2.67 times, thus making the layer successfully fit on the device. Logic shrinkage also doesn't require significant slowdowns in training speed. Despite the fact that logic shrinkage introduces additional matrix vector multiplications for every forward propagation during training, the slowdown in training speed per epoch is minor. This is achieved thanks to the highly optimized linear algebra routines provided by GPUs. In conclusion, we introduced logic shrinkage, the automated search for and implementation of LUT-based neural network accelerators in which LUTs, sizes, and inputs are learned during training. The authors of prior NAS works pursued a top-down approach, learning an intermediate representation, a network topology, while leaving its hardware mapping as a separate task. In contrast, we propose a bottom-up, hardware-aware alternative, directly learning a netlist as the topology, with the flexibility of a target platform exposed to the training process. We show that our proposed method, logic shrinkage, is lightweight, and it can result in the production of netlists that suit FPGAs very well. We analyzed hundreds of experimental results, and we found significant area accuracy trade-off improvements over previous works. For more details, please check out our paper and our free open source software on GitHub. Thank you for listening.